Okay, hello guys, it's Orange. Today we are going to do again a bit of structural analysis. Okay, in our new video we are going to analyze a simple supported beam again, but with a uniform distributed load on it. This is the load Q 4 kN per meter. We will consider this point to be our point B. Here the middle span to be the point C. Here the other extremity to be point B. Okay, so the objective is to find and draw the shear force and the bending moment diagram. So we are going to find and analyze the structure. At the end we draw the shear force and the bending moment diagram. Okay, so first step, as usually, we start by the free body diagram. How do you get the free body diagram? By removing the support that we have. Removing the support, we have this free body diagram that's with AY, AX and BY. Here we have two external reaction forces because we have a hinge support, and here we have only one external reaction force because we have a roller support. This is the reference frame that we we'll consider in the case of our analysis to be the positive reference frame. Okay, yeah. Second step, we look for the external reaction forces. The external reaction forces, the summation of forces along the x-axis, we will have AX is equal to 0 kN. Actually, as you can see here on the free body diagram, AX is the only force applied on the horizontal axis, which is AX, and here we apply now the summation of forces on the y-axis, which is equal to 0. We will have AY plus BY. AY and BY are pointing upward. According to our reference plane, we will have them to be positive, and then we have the load, the uniform load applied on the whole structure. That will be defined by multiplying the load Q times the length of the beam. The length of the beam, that's QL. That, and since it's pointing downward, we will have it to be negative. That's why we have negative QL here, because you will have to find the load, the whole load that is applied on the beam. It will be as if you are working with the concentrated load. That's why we make Q the load per unit length times the length to have the load that is applied on the whole load. That's it. So we have at the end of the AY plus BY, which is equal to QL, and due to the condition of static equilibrium, you have to satisfy the equilibrium condition. In fact, you have AY which is equal to BY which is equal to QL or over 2. Okay, so AY is equal to BY which is equal to 8 kN because we have Q to be 4 kN per meter, and L the length which is 4 meter. Okay, so remember here we were able to write it like this because we are trying to satisfy the equilibrium condition. Otherwise, we were supposed to write the third static equilibrium equation, that's the summation of moment along a specific axis, and then find one of those unknown and come and substitute there to have the second one, because our two unknown there was AY and BY. Okay, the next point, now we are done with the external reaction forces. We go for the internal reaction forces. For the internal reaction forces, how do we get the internal reaction forces? By making a cut on our structure. So we say let's consider a cut from A at a distance x from A with x within 0 to L. Remember, here we have a uniform distributed load. So the reaction of our structure in response to the load that are exerted, or the forces that are exerted on it, will be the same all over the span. That's why we are taking the cut here all over the span. That's why x is between 0 to L. So we draw the cut, and here you can represent the internal reaction forces, which is the bending moment and the shear force. Okay, we don't need to represent again AX here. That's the external reaction forces along the x direction because it's already equal to 0. So now we are looking for the shear force, which is the internal reaction force. This summation of forces along the y-axis will be equal to 0. So you have AY is pointing upward according to our reference frame. AY is pointing upward, is positive, and you have shear force is negative because the shear force is pointing downward. So you have negative shear force minus QS. QS here represents again the load applied on that on that portion that we have cut of the structure. That's why we have cure X, as we did for the case of the external forces here. So we have to find the load that is applied on this portion that we have cut, and to have it we have to multiply the unit load, that the load per meter length, that's 4 kilonewton, times the portion that the length of the portion that we have got, which is X. That's why we have cure X at this level, and since the load is applying is pointing downward, that's why we have negative. Okay, so at the end of the day you have the shear force is equal to cure X minus AY. So you have shear force is equal to 4X minus 8, which is in kilonewton. Okay, since it's a force. And now we are looking for the bending moment. Now the bending moment, to have the bending moment, we apply the summation of moment around the x-axis is equal to 0. Here we have to look for the moment of each force is applied on the section. So we have AY, we will look for the moment AY. AY here we will use this direction sign to be our positive conventional sign of direction. So this one will be considered as our positive sign of rotation. Okay, so here we have now what? We have AY, which is following the direction of the positive direction of rotation. You have AY, which is rotating around our point of axis of rotation here, which is positive, is in the same direction, and the distance from the axis, the direction of the vector AY, because it's a force, so the distance between the direction of AY and the axis of rotation here is X. That's why we have AY times X to have the moment AY. And then also we have now the moment. We are looking for the moment of the load applied on the uniform distributed beam, right? Uniform distributed load. So this load now, how do you get it? We will have to multiply. We will have to find the load first of all that is applied on this whole structure, multiplying the unit load, that's cure, times the length. First of all, the length of our section here is X, so we have first of all cure X, and since it's pointing downward, you can see that it's going in the positive direction of rotation that we have chosen. No, it's going in the negative direction, because actually if you are to look this arrow, if you are to make it rotate around this point, this axis of rotation, you will go in opposite to the direction of rotation that we shows as positive direction of rotation. So that's why we have negative here. And now you have, since it's a moment, we are supposed to multiply it times the distance. For the distance now, we are considering the middle span of the portion of the structure that we have, of the portion of the section, in fact. So here we will find the center of gravity, and the distance here will be x over 2. So the x over 2 will multiply it times the load that is applied on the section, this section x. It will give us this expression, this negative cure X times X over 2. And now we have the bending moment. The bending moment is opposite to the direction, the positive direction of rotation. So the bending moment will be negative. That's where we found that expression. And at the end of the day, the expression of the at the end of the day, the expression of the bending moment will be equal to cure X squared over 2 minus AY(x), which will be substituted and we will have this expression. Bending moment is equal to 2x squared minus 8x. Okay, something that's the final expression is in kilonewton meter. So something that you have to know to check if you are you did everything in the good manner, you can differentiate the expression of the bending moment and make sure that you find the expression of the shear force. So if you differentiate 2x squared minus 8x, you will find 4x minus 8. And if you differentiate also the expression of the shear force, you will find exactly the unit load applied on our structure, that's 4 kilonewton per meter. So we can conclude that the analysis was well done. Now we can go and draw the shear force diagram and the bending moment diagram. Okay, as I used to explain, there is a small easier way to do it by drawing this table to help you have some point of your graph. So here I consider point A at x equal to 0, point C at x equal to 2 and a point B at x equal to 4. Point C is the middle span actually corresponding to the middle span of your beam. Okay, so here you have the shear force equation. Here, normally as usual the table is made in such a way that the first column corresponds to the forces and the other column corresponds to the various points that you choose to plot your diagram. So the first line now here will correspond to a shear force equation or the shear force expression, which is 4x minus 8. If you substitute x by 0, you have negative 8 here, and if at point C at x equal to 2, if you substitute x by 2 here, you have 0. So at x also equal to 4 now at point B, which corresponds to point B, the other extremity of our structure, you have the shear force equal to 8. So as we said, at point A, x equal to 0, we are at negative 8. So this is our negative 8 here. No need is corresponding to negative 8 kilonewton, but no need to put the negative since we are already downward here. So at point A we have negative 8, and at point 2, which corresponds to the middle span of our structure, we are at 0. That's the 0 here. And also at point B now, which corresponds to the other extremity, we are at exactly 8. So this is here, this is the 8 represent, and we join all the points. So this is the shear force. This is our shear force diagram. And now for the bending moment diagram, actually we have at point A at x equal to 0, you have what? You have the bending moment will be equal to 0. So we are here at x equal to 0, you are at this point. Okay, and now at point C equal for x equal to 2, that's the middle span of the structure, you have x is equal to negative 8 kilonewton meter. That's negative 8 kilonewton meter. So that's the negative 8 that is represented here. No need to put the sign again, as I said. And now for the third point, you have point B at x equal to 4 meter. You have the bending moment here will be equal to 0, which is here, and then you just join the 3 point.